So in this video, I wanted to go ahead and give another example of solving a second-order differential equation that involves a damping coefficient that is not zero. So in other words, we have a set of mechanical vibrations or harmonic oscillations that has some sort of force opposing the velocity. And so as a result, we expect that this spring mass system will eventually come to some sort of rest. So in other words, if even though I have a spring mass constant or a spring constant of 60 newtons per meter and a mass attached to that of 20 kilograms, I also have a damping coefficient of 100 kilograms per meter. So basically, this system is being somehow halted by some sort of force. So as you might imagine, this would probably involve some sort of maybe in the verbiage of working with cars, we have some sort of spring attached. There's a mass at the bottom, but there's something that's sort of pushing that or kind of keeping it from continuously oscillating. So we have some sort of friction. Now, by the way, this friction, this dampening or damping item in this system could be some sort of force of gravity. So damping is not just limited by some sort of external device, but it could actually be a result of forces that are acting on the system in different ways. Probably the most simple example of that is a system where you do have a spring attached, a mass attached to a spring, and there is something kind of inhibiting the motion of that spring. Okay, so we set up our system, and in this case, our system is the second derivative, and we've learned that to derive this, we end up with this equation up here, which we've done. B over m, well, B is 100 and m is 20. We'll go ahead and substitute those values in. And then we also have that K is 60, so we have a ratio of 60 over 20. So what we need to emphasize here is the fact that it really doesn't matter how big these values are. The bigger the mass, the smaller these coefficients will be, right? Because we're dividing by m in the coefficients for either term. So as a result, if even though you might have a gigantic damping coefficient b, as long as the mass is really, really large, then the damping doesn't really affect it all that much. So imagine that you have a 2,000 kilogram mass attached to a spring, and you have a damping force of 100 kilograms per meter. That damping force is not going to be that effective in reducing the oscillations in that system, or at least not immediately as time passes by. So the first thing we want to do mathematically is we want to reduce this to the simplest form so that it's very simple to work with. So we just do the arithmetic here and reduce this to the following system. Okay, well now we would proceed to actually solve this. And remember, our solution is based on a guess. And we determined that the best guess in this situation would not be sine or cosine. And the reason for that is because if you look at sine as the original function, the derivative of sine is cosine, and the derivative of cosine involves sine. So adding up sine, cosine together, you're not going to be able to get zero, because keep in mind that even if there is a phase shift, the derivative will still have that phase shift in it. So all three of these functions, well, excuse me, these two will be in phase, sinusoidal functions, but this will be out of phase. And as a result, you're not going to be able to add them up and get exactly zero all the time. So our guess that we've chosen is the other guess that we have, which is an exponential function, but we're going to guess e to the RT. And the reason we guess e to the RT is, one, because when we take the derivative of e to the RT, assuming that this exponent is negative, well, then the derivative is going to involve a negative coefficient, and the second derivative is going to involve, again, a positive coefficient. So the only way to get these to cancel out and produce zero as a result is by having at least one opposing sign somewhere in the system. So we'll now focus on that. And so our process for doing this is going to be to solve this and basically say, let's assume that y equals e to the RT. Well, if that's going to be our guess, then the derivative of our guess, dy dt, is going to be r times e to the RT, using the chain rule. And the second derivative of e to the RT, i.e. the derivative of r e to the RT, is going to be r times r e to the RT, which is the same thing as r squared e to the RT. So now these guesses don't always work, but when they do, or the way we know they do, is we can plug them back into this equation and find a value of r that will solve this equation. Okay, well, we proceed to do that. So I'm going to replace the terms in this derivative. This is r squared e to the RT based on my guess. And dy dt is going to be r e to the RT based on our guess. And plus 3 times y, which is e to the RT based on our guess, is equal to 0. And so now, if assuming I can solve this, I can find an r value that will allow these three terms to cancel out and become 0. But I need to know what value of r I'm working with. Okay, so to figure that out, now this becomes a mathematical problem. This becomes an algebraic problem. And so algebraically, one of the first things I do is try to factor this thing, and I can do that. I can factor it into e to the RT. In other words, pull out e to the RT from each term, and I come up with a valuable product, which is e to the RT times quantity r squared plus 5r plus 3, and that equals 0. And the reason I want to factor this is because I know that this left-hand side will be 0 when either this term is 0, this factor, is 0, or when this factor is 0. Now, what I know about this is e to the RT cannot equal 0. There's no way for that. In fact, if I tried to solve the equation, e to the RT equals 0, well, okay, I need to solve for r. So I get, let's see here, I take the natural log of both sides, right? Natural log of e to the RT, and then I need to take the natural log of 0. But wait a minute, the natural log of 0 is undefined. We can't take the natural log of 0, so therefore that is a proof for why e to the RT can never be 0. E to the RT can at best be a decaying function that approaches 0 in the long run but never reaches it. It's asymptotic towards 0. Okay, so the only other option is to say, okay, well, this left-hand side will be 0 if r squared plus 5r plus 3 equals 0. And this, my friends, is a quadratic function, equation, or function, I guess, quadratic equation which involves solving for r. So what values of r will make this expression, this expression right here equal to 0? Well, this involves using the quadratic formula, and we know that the quadratic formula is r equals, because we're not using x, negative b plus or minus the square root of b squared minus 4ac all over 2a, where a, b, and c are, well, wait a minute, that's the coefficient here, which is 1. The coefficient here is 5, and the constant here is 3. So a equals 1, b equals 5, and c equals 3. So I can use that, and provided I do the algebra correctly, I'll be in good shape. Well, let me just go ahead and set it up. I have negative 5 plus or minus the square root of 25 minus 4 times 1 times 3, which is 4 times 3, which is 12. And that's good. I get a positive under the square root. This is something to keep in mind. I've got to have a positive under the square root because I can't square root negative numbers without going into the imaginary realm. And you don't want to go into the imaginary realm if at all possible. Okay, so this would mean r equals negative 5 plus or minus the square root of 13, which is a square root of a real number, which is going to be real. A positive real number, which is going to be real, divided by 2. Now, alternatively, I could use technology to find this, and technologically, if I plotted x squared plus 5x plus 3, it's a parabola, and I'm using Desmos here, so I could quickly just kind of jump to the solutions and get it to 3 decimal places. I get, if r, or I guess in this case I have up here, x equals negative 4.303 or negative 0.697. Those are my solutions, and those are the same things I should get out of this equation. So r is approximately negative 4.303, or r is negative 0.697. I'll just abbreviate these R1 and R2 arbitrarily. Well, I know that y1, one possible solution is going to be to take k1 e to the r1t, and another solution is going to be y2 equals k2 e to the r2t. And I also know by superposition that I can superposition these things, if you will, and I can actually form a sum of these two equations and get a new solution. So, okay, well, what does this become? This is k1 e to the negative 4.303t, and this one is k2 e to the negative 0.697t. And now I have my final solution. My general solution is going to be k1 e to the negative 4.303t plus k2 e to the negative 0.697t. Now, these two arbitrary constants are going to be used to satisfy the initial conditions, which are these ones up here. I want to have an initial displacement of 0.5 meters. Now, if we think about that, that's going to be a stretch of 0.5 meters. So it's, compression. So the spring is compressed, but where's it moving? Well, it's moving in the negative direction, which means it's actually compressed right up here, but it's actually moving downwards at a rate of negative 0.3 meters per second. So when I visualize the solution, I should be able to see that. So I have 0.5 and negative 0.3. And so I know that I could set the position function. I want the position to be 0.5 equals k1 e to the 0, because I'm looking at this at time 0, plus k2 e to the 0. And then the derivative of this guy, this is the position function. The velocity function is the derivative of the position function, and that's going to be y prime equals negative 4.303 k1 e to the negative 4.303. Whoa, I don't know what happened there. T plus the derivative of the second term, which is negative 0.697 times e to the negative 0.697t. And of course, I forgot the k2 here. And so now I can set the second equation. Now we decided that we wanted that initial velocity to be negative 0.3. So I'm going to set the velocity equal to negative 0.3, and I'm going to set time equal to 0. So guess what I'm going to get? Negative 4.303 k1 minus 0.697 k2. And now I have a system of equations. That just means that I need to make sure that k1 and k2 satisfies both of them. So I'm going to write these down together. 0.5 needs to equal k1 plus k2, and negative 0.3 needs to equal negative 4.3. I'm just going to make this rounded off to the tenths place to make it easier, minus 0.7 k2, and now I need to solve this system. Well, how do I do it? Well, from algebra, we can solve for one of the variables in one of the equations, and that's easiest to do in the first equation. So k1 is equal to 0.5 minus k2. And now I can use this and plug it into the second equation and get negative 0.3 equals negative 4.3 times k1. Well, k1 is 0.5 minus k2 minus 0.7 k2. And negative 4.3 times 0.5 is going to be half of negative 4.3, which is negative 2.15 plus 4.3 k2 minus 0.7 k2. And now I'll combine my like terms, and I've got the equation in terms of just k2. So I have negative 2.15 plus 3.6 k2 equals negative 0.3, and I can move the 2.15 to the other side, and I get, let's see, 1.85 positive equals 3.6 k2, and I can divide both sides by that value, and I can actually use decimals to find this for me. 1.85 divided by 3.6, and I should get an answer which is 0.5. About 0.5, so we'll go ahead and round it. So k2 is about 0.5. There I have my coefficient. Now I know that k2 is 0.5 satisfies both equations, so since that's the case, well, I rounded. So since K2 is 0.5, that would mean K1 is approximately 0, meaning that that coefficient can approximately